start with state observer design part 2. In this we will study effects of addition of the observer on a closed loop system, then selection of observer poles and controller poles, and we will see MATLAB programs. Now, about the effects of addition of observer on a closed loop system. That means what is happened here, that we have a system, and for the system we have a controller. Along with this controller we have observer. So, we have observer controller. So, we have to see that if you design an observer, so is it affected to the controller poles or vice versa. So, that part we have to see. So, first of all we draw the block diagram of a system with observer, that is observer state feedback control system. Now, here is the observer, here is A matrix, here observer controller matrix KE, now here is the B matrix of an observer. Now, about the system. This is C matrix, here is the actual output Y, here is A matrix again of a system, now here is B matrix, and now the U is common, and here is state XC, and its controller is going for this state controller KC, and here is the output Y. And this is input U, and this is same U. Sign positive positive, here is positive, C matrix. So, you will find that the upper portion, this portion, you can see that this is your system, there is actual system, and this portion is observer. Now, the output of the observer system is YE, and here is output Y, and here we are reducing the error between Y and Y, and there are two matrices, or we can say two controller matrices KE and KC. This KE is for observer, and KC we can say this KC is for our controller. Now, we have to see the effect of this KC and KE. Are the KC and KE are related? That is, suppose if you change the KE, can it affect the KC or vice versa? Now, we start deriving the result. So, here x dot equal to Ax plus Bu and y equal to Cx. Now, here the control law, your control law is, now our control law is u equal to minus kc into xc. So, after this you to replace u equal to minus kc into xc in these equations. So, you will get x dot equal to ax minus b kc into xc. Now, here one factor we added, ax minus b kc into x plus b into kc into x minus b into kc into xc. Now, here a minus b kc into x plus b into kc common x minus xc. So, you will find that x minus xc, this factor, this is nothing but the error. Therefore, we write E equal to x minus xc. Therefore, we will get x dot equal to a minus b kc into x plus b kc. So, this is the equations which we have obtained from the given observer's state feedback block diagram, and based on the control law, these results we have obtained. Last time we have also determined the error equations. So, the observer error equation that is equal to E dot equal to a minus kc into E, this is error equations. So, now we have got equation for x dot, and we have got the observer error equation E dot, equation 2. Now, we combine two equations. So, we will get x dot E dot equal to a minus b kc bkc 0 as a minus k into c, and here x and e. Now, we have got a equation in terms of x dot and e dot, and now here is to determine the response or check the stability or to determine the eigenvalues. Now, we have to consider these equations. So, this is similar to our equation, let us say x dot equal to Ax. Now, here A is like this. That means, here we have to determine the characteristic equation for this system. The characteristic equation for this system is given as Si minus a minus b kc minus b into kc 0 Si minus a plus k into c equal to 0, and now here in terms of determinant we will get Si minus a plus b into kc, and here Si minus a plus k into c. So, after doing the calculations, we found that the such type of equations we got, and here we will find that this particular first part, let us say this first part, let us say x, and this is a y part. So, x part consists of the eigenvalues with respect to kc, that is a controller kc, and part y which consists of a controller k, and as far as the eigenvalues of this is totally dependent, that means this can be equal to 0 or this can be equal to 0. That means the both these equations individually, if you take, they are independent. Therefore, we will find that whatever changes you can make in this kc, it is not affecting the k, and similarly whatever changes you can make in the Ke, it will not affect our Kc. That means whatever poles we design, that is whatever controller poles we have fixed, and whatever with the observer poles we fix, both are independent, they are not dependent to each other. Therefore, there is no any such issue while designing the controller. That is the most important advantage of this type of controller design. Now about the next part, selection of observer poles and controller poles. Just now we have seen that the observer controller matrix, that is say Ke, and controller matrix Kc, both are independent. That means you can place poles, control poles anywhere in the space. Similarly, you can place the observer poles anywhere in the space. But still, is there need for any selection? Is there any selection issue related to it? Generally, it is said that your observer poles should be 2 to 5 times far away from the control poles. That means it has been said that, let us say I am taking 2 poles. Now here OB, this is nothing but the observer poles, and now here these poles, let us say OC. So OC indicate you have a controller poles, and here these are observer poles. That means as we are selecting observer poles far away from the imaginary axis, and in terms of magnitude they are greater than controller poles. So these poles directly reach or easily reach to steady state in comparison to the control poles, and therefore overall system, if you can consider, it is dominated by the control poles. So generally we are following this type of things, but sometimes there can be issue, that is there can be a problem with the sensor, that output can be noisy. Then if the output is noisy, it means that there is a issues with respect to the measurement. So in that case, if you take observer pole very far away, so it may amplify, and therefore our observation is not proper. So in that case, what we are doing, we are keeping the observer pole near to the imaginary axis as compared to the control pole. Therefore in that case your response is dominated by the observer poles only. So as far as any system is there, you have to try a different set of value and see the which gives the better results, and finally the that is which to be taken, that is a trade off between your speed of response as well as the effect of noise or disturbance. Now we will see some MATLAB programs with respect to this controller poles as well as the observer poles. Now our main purpose is to design a controller using a MATLAB. So y dot equal to ax plus bu. Now this is a plant, and y equal to cx. Now when we are designing a state feedback controller, so in that state feedback controller design, we are concerned with the controller. That controller, because of this controller we can place the pole anywhere in the space. So in MATLAB there are 2 commands, one command that is called ecker, ECKER, and place, but both the command can be used for designing of the controller. But for SISO system, single input single output, we are going for ecker, that is for SISO, and if the system of MIMO, we have to go to the place command, and the general format for this controller design is KC equal to ecker A poles, sorry, A matrix, B matrix, and DP, and here DP is the desired pole, That means at which location we want the poles. For example, if you want the poles say at this point, say -1, -2, so we can say that your dp is -1, -2, and if you use this command directly you will get the control matrix. That is, a single step or single command is sufficient to get the controller matrix. Similarly, you can get the controller by using a place PLACE. So, A comma B comma dp. So, you will get the controller using the place command, but for MI mode definitely we go for place, and for SISO we have to go for echo command. But when we are designing the controller for any system, the first step is to check the controllability of the system. Therefore, for any plant AX plus BU, write the command as controller matrix or controllability matrix as CTRB A comma B, and we have to determine the determinant of QC. If the determinant of QC, that means this QC gives you the matrix, that is the controllability matrix, and then we have to take the determinant. So, command we have to use DT QC. So, if it is non-zero, then we can say that control design is possible, and then you have to use the command occur or place. If this determinant of KC is equal to 0, it means that controller design is not possible, and therefore we will stop here itself. Suppose if you take a system matrix as 0 1 -2 -3, B matrix as 0 1 and C matrix as 1 0. Now the first step we have to check the controllability of the system. So, controllability QC equal to CTRB A comma B. So, first of all here we have to define A, that is 0 1 -2 -3, and here we have to define the B as 0 1, and then after A and B we have to use command QC equal to CTRB A comma B. We have to write determinant of QC, and it will get as -1, and therefore we can say that controller design is possible. Now, about the controller KC, the command is ACKER A comma B comma a DP. Now, here DP is the pole placement. So, prior to this one we have to use the command DP as -9 -10. This is the desired pole placement, and therefore you will get the controller KC equal to 88 16. So, in this way we have designed a controller for state space model, and the model is SISO system. So, first of all what we have done, we have checked the controllability of the system, and then the system is controllable, and then we have used the command KC equal to occur A comma B comma DP, and this is the controller which we have got. Now, we have already seen one equation, there is x dot E dot equal to A minus B KC, and here B KC 0 A minus K into C, and here X E, and there is a condition, that is X 0 and E 0. Let us say a condition is any value, let us say 1 2 3 4. Now, here our purpose is to determine the state response as well as the error response. And what is our basic idea is that about the states, state will start and it should quickly reach to the origin or 0. Similarly, error is there, error between the actual state and the estimated state, that must be reached to 0 quickly. So, this is our aim, and therefore, we have to determine the response of the all states as well as the error response. Now, we assume that this is our system, this is the involvement of error equation as well as the system equation, whereas the involvement of we have a controller as well as the observer, and here we have to develop the MATLAB program. Now, we assume that this A matrix is 2 cross 2, assume that this A is a matrix 2 cross 2 matrix. So, A is 2 cross 2 matrix, it means that there are 2 states, that means x1, x2, and here error is also E1 and E2. That means here we have to determine the response of state x1 with respect to t, state x2 with respect to t, and we have error E1 with respect to t, and here error E2 with respect to t. And what we want, that all these errors, all the state response should reach to 0 quickly. That means, let us say this is 0, that means whatever response start, it will move like this. Similarly for here, similarly for here, and similarly for here also. That means this is the origin, this is the requirement, and for that purpose, means whether we are getting this type of response or not, we have to do the MATLAB program. So, when we are doing the MATLAB program for such type of things, here we required the 2 controllers. One is the controller of the actual system, and other controller because of the observer poles, and therefore, the first part we have to write down the KC, a command occur ACKER, A matrix, B matrix, and this is a DP. So, DP means the actual pole placement of the controller. A is the system matrix, that is this of x dot equal to AX plus BU. So, A is the system matrix, B input matrix, and here DP is the desired poles. Now, after this we want the observer controller. So, observer controller matrix, that is KE, we have to use the same command occur ACKER, we have A transpose, that is A dash, C transpose means C dash, and let us say L transpose, that is L complete system transpose, that gives you the observer controller matrix, that is in that case C is Y equal to Cx. So, as per the this equation about the observer and control equation, we have got Kc and we have got the Ke. Now, we have to represent the complete system, this system, into the state space form, and therefore, here the command we have to use sys equal to ess A minus B multiplied by star K C, B star multiplication of K C, then zeros 2 comma 2, and here A minus K E multiplied by C. So, here this particular part is nothing but this equation, that is A minus B into Kc, B into Kc 0, A minus K into C, that is a complete matrix, but there are B, C, D matrix. So, they are represented by I4, and this is I4, and here the bracket completed and this complete bracket. So, this particular part gives you the given system into the state space form. So, I4 it means that you are getting the identity matrix, that means you are get the element in the diagonal form. So, here afterward we have to define a time, assume that t equal to 0, 0.01, say 10, assume that we have taken the t 10. Here you find that we have taken 2 by 2 because we assume that here A is 2 cross 2 matrix, is belong to 2 cross 2 matrix, and I4 4 is variable is we have written because here x involved 2 state variable, error there are 2, therefore we for complete matrix we have 4 cross 4. So, in order to get this we have written I4, I4 and I4. Now, here t has been defined. Now, in order to get the response, let us say m is equal to initial, this is the initial command. Now, this sys, now the initial conditions. So, here initial condition we have taken 1, 2, 3, 4. So, we return 1, 2, 3, 4, t bracket complete. So, this is the initial command where it shows the response of complete plant, but now our purpose is to get the response of an individual system, that means individual state as well as individual error. Therefore, we write this x1 is equal to 1 0 0 0 into m transpose m dash. So, that gives you the response of state x1. Now, if you write x2 0 1 0 0, this gives response of state x2, and then error e1 equal to 0 0 1 0, there is m dash, that is the response because of the error e1, then e2 is the 0 0 0 1 to m dash, this is the response of the error e2. So, all the 4 response x1, x2, e1, e2 we have shown. So, this is the result in terms of numerical we have got, but still we have not got any graphical picture, that means we have to show all this result in a graph. That means the command to be used to get the result, that is a plot, that is plot command is to be used. And so, here there are 4 responses. So, all these 4 responses we can draw on a single plot, or we can take all these 4 plot on a single graph, or a single window we can show all this, or individual windows can be taken. But now, here we want all these results in one window or one graph. Therefore, here we had to use the command subplot. Therefore, here the command to be used subplot 411. So, subplot 411 it indicates that there are 4 rows, that means these are 4 rows 1 2 3 4, 1 this is a column. So, 4 rows 1 column, and this 1 is the first positions. So, where we will get the graph, therefore, we write the command plot t comma x1. Now, we have got this response of this x1. Now, about x2. So, here we have to write the command subplot 4 rows 1 column, and this position is second. So, we write 412 plot t comma x2. Similarly, for error e1 and e2 we can write down as subplot 4 1 3 plot t comma e1. Then here we can write command subplot 4 1 4 plot t comma e2. So, using this concept, you can get the response of all state as well as the error. So, all this type of programming is very much essential when we are doing the complete analysis of the system. It is because even though there is an error, if the error is not coming to origin or there is an error, it takes a lot of time to reach the steady state, that means that we do not require. Therefore, this type of analysis using MATLAB is very much required. Now, you see these are some references. There is Ogata, D. Roy Choudhury and Stefani. Thank you.